We'll go into the next lecture, which is talking about how do we determine the so-called interdiffusion, d delta, for a alloy system that is not interstitial diffusion. Okay, how do we determine that? By the so-called method of Matano analysis. Okay, so before we do that, let's first think about how do we get diffusion coefficient if we have so-called analytical solutions. So we are dealing with, in one case, spin-ion dopant case, put a fixed amount of dopant onto the element, onto a long piece of material, and the so-called semi-infinite bar. We have fixed amount far away, there will be no change in the concentration, okay? And we can put a radioactive tracer. And typically we are talking about dilute solution, which is either interstitial or substitutional, which we have the system interdiffusion coefficient would be the same as the intrinsic for one of the system, which is the solute one, the really dilute one, right? Which is the same as the your radioactive tracer. Whatever you measured from radioactive tracer would give you the diffusion coefficient. Make sense? And then remember, for this so-called semi-infinite bar diffusion with a fixed amount at the surface for initial diffusion, 0 far away, and boundary condition far away, the concentration doesn't change. There will be so-called analytical solution. C for concentration is a function of both location and the time is given by this equation. What does N mean? The total fixed amount that you initially put onto the surface, okay, square root of pi times dt times exponential of x squared divided by 4 dt minus, which means at any given time t, at any given location x, you can mathematically describe the concentration. Make sense? So then, let's say for any given time t, at time 0, you put it on, you drive it in. After given time t1, if you measure the concentration profile, right? It's a radioactive tracer. How do you measure it? You can use certain method to measure it. Or even if it's not radioactive tracer, let's say interstitial, you may be using like, let's say XPS depth profiling, OJ electron depth profiling, or Sims depth profiling, quantitative. You have some information like this. The change of concentration with respect to location, you detect it across the depths. You get a certain curve that looks like this. And then what do? Well, if I have an analytical equation, I'm going to do curve fitting. Quite often you're going to do curve fitting. So what did I do? This is our analytical equation, right? Take natural log for a given time t, which means you already know t1, right? Take natural log of the left side, and the right side will be natural log of n over square root of pi dt1 exponential natural log got cancelled, right? Minus 1 over 4 dt1 x squared. What does this mean? This means, okay, if I at any given time t1, I have this curve, can you plot log c versus x squared? You have x, right? You have c. For each of these points, you will know the c, you will know the x. You also know t1, so I can plot so-called log and natural log of c versus x squared. And if I do that, the slope would be what? Yeah, it would just be in front of this guy, right? The slope would be just minus 1 over dt1. So you for a fixed time t, you get a concentration profile, you fit it, and you can get the diffusion coefficient. And if it's very dilute, that is just your intrinsic diffusion coefficient, which is also your so-called interdiffusion coefficient. Make sense? That will be the case if you have a ideal diffusion scenario, zero concentration in the beginning, fixed amount towards the end, zero far away from the interface, fixed amount at the surface. That will be analytical solution. Of course, we assume that the diffusion coefficient doesn't change with concentration. Why? Because everything we are assuming is very, very dilute. Make sense? That's some assumptions. When we did this analytical solution, we assume the diffusion coefficient does not change with concentration, and it applies only when it is very, very dilute. Okay? So in the interest of time, let's just stop here.